Okay, so good morning. That was kind of better than yesterday, wasn't it? You can kind of realise.
It was after lunch though, wasn't it?
It was after lunch, but I guess now they understood the protocol, right? If you say good morning, people answer, right? So my name's Andy. I'm going to be talking to you about TPL Dataflow. Anybody played with TPL Dataflow before? A couple of you?
Yes.
Yeah, a few of you? Okay. So for some of you, this will be completely new, hopefully. The title, Brand New World of Asynchronous Programming. That wasn't my original title. The conference organisers decided my TPL Dataflow title wasn't sexy enough, okay? And therefore people wouldn't attend. Maybe they're right, okay? So we renamed it to Brand New World of Asynchronous Programming, okay? It's not really true. A lot of these techniques have been around for a very long time. You can go back to papers, I think in the 70s, where people were pushing this general idea, so it's not really that. Richard is my code monkey, okay? His job in life is to do what I tell him to do. He has no free will. You will see that it's just a myth, okay? His job is to do whatever I tell him to do. When I click my fingers, he will progress the slides. It's not abuse, it's just a general program, okay? So we're going to talk a bit about why we need to care about TPL Dataflow, some of the motivation behind it. Then we'll talk about how you can get it. Well, that's a new get, that's been pretty quick and easy. And then we'll actually start playing, we'll start building some apps with it, various things. And we'll try around some various standard kind of problems, producer, consumer, we'll do some image processing with it, some pipeline kind of powerism. And I'll finish off with a problem you may be familiar with, dining philosopher's problem. You all heard of that one? Yeah. I hope so, because that's why I picked it. Okay. If you've been computer science, I'm sure you all have heard it. Okay. So, traditionally, if you go wrong back a whole period of time, when you started programming, the concept of thread was very foreign to you. You just wrote a program that ran on the main thread and it executed sequentially, and every time you ran it, you generally got exactly the same result. Okay? So very predictable. The moment we started to want to have more throughput for a machine, we started to say, well, we'll have lots of threads of execution. But our model was to take conventional programming style and just throw threads at it. So now we've got lots of sequential programs all running in parallel, effectively. That's what we've got. And as long as each one of those threads of execution is in complete isolation from each other, life's really easy. The problem is, though, that generally isn't what happens, is it? Most often we have a situation where I want to have lots of things running, but they're going to share some state. And obviously the problem is if you share state, is we have to synchronize. So we have to effectively make sure that multiple threads aren't updating the state at any one period of time. Okay. Now, once we throw synchronization into the mix, things start getting complex. Yes, if you came yesterday, I showed you how to make things simple. But in reality, they are quite complex. A different way of doing concurrency is to say, well, rather than have a thread of execution that effectively goes through separate objects along its way, why don't we say this, that each object is completely autonomous. You have a thread of execution inside each object. And the way you communicate between each of those objects is through message passing. And that's more like the real world, right? You know, effectively, if you interact with the toaster, suddenly your execution doesn't stop while the toaster's waiting to pop up the bread, right? You can do other things while that's happening. That's a more conventional style of program. So this is the kind of model that we're talking about. We're talking about multiple objects where they have their own internal state, and each object has its own thread of execution. And if the only thing can update its state is its own single thread, is there any issue? Shouldn't be, because if that's the only object, that's the only thread that can update the state, life is good. The way they talk to other objects is by sending asynchronous messages. They'll send a message to another object, they don't care about whether the object's acted on it, as far as they're concerned, they send the message. And now we get concurrency through lots of objects running on their own separate threads, all handling their own individual messages. Yeah? Sounds like a nice dream? Yeah? Do you all dream about code at night? Come up with new features? No? Okay. Yeah. Okay, so here we've got a very simple kind of programming example. Okay? So I want to process a database rows. Talking to the database is inherently sequential. Right? Trying to execute a query in parallel, you need to have some very elaborate forms of SQL in order to do that. So I want to load a row from the database, I want to transform the data, I want to batch them up, and I want to send them off to a web server. That's the problem space I'm trying to do. But I like to do that efficiently, I like to parallelize that. Maybe I can parallelize the transformation process. Talking to the database is inherently sequential. The actual processing of the data I can probably parallelize. You know, and I could use various things like parallel.for, parallel.for each until to do that. But if I care about order, then maybe that's a problem, right? So if I care that the first row that comes in, having been processed, put into a batch, and goes out to the web server, has to be the first record that goes to the web server, and I try and process multiple records in parallel, the order's not guaranteed. Parallelism is easy if I don't care about order. But if I want to care about order, then that kind of makes things a little bit more tricky. However, there's a kind of a standard way of solving this problem. In fact, it goes back to the 1900s. Henry Ford when he decided to commercialize automotive cars, so we could effectively all own a car, he built a production line. Okay? With the idea here being that effectively every stage of that production line has a different set of workers working on each part of that car. So in that problem we just talked about, we can do the same thing. We can say we're going to have a block of code that's purely responsible for talking to the database. And it goes and reads on a single thread a row from the database. Once it's read a row, it sends that row to another block called the transform block. That transform block is going to transform the data. When it's finished, it's going to send a message to the batch block, whose job in life is to keep receiving transformed blocks until it gets to a certain size. And then it hands it over to a piece of code that's responsible for talking to the web service. If each one of those blocks is running on a separate thread, while we're processing the second row from the database, we're currently transforming the first row. While we're processing the third row from the database, hopefully, we're actually got the first row into the batch and we're actually transforming the second row. Okay? And after we've done through 4 of those different time slices, we end up with a situation, effectively, hopefully, that we start sending stuff out at some certain period of time. Okay? So we've got separate threads of execution. We're executing this in parallel, but the important thing here is we're guaranteeing order. Yeah? You can't suddenly, the first message that gets from the database is always the first message that's going to get left on the web service. Order is preserved. Okay? Yeah? What's the problem with this thing? Will this parallelize nicely? It's nice and simple. We just pass in messages around. There's no shared state. There's no locking involved. What's the issue?
You want to aggregate things?
Sorry?
If you want to aggregate things in batch?
Well, they've got a batch thing. That thing batches there. Yeah? So it receives, when you've got 10, it sends it to the web service, and then the web service sends a batch. But ultimately, for this to really work properly in Henry Ford's environment, if a given stage of the production line took twice as long as any other stage, would there be a problem? Yeah, you end up having this huge amount of things building up behind these workers. How could he solve that problem? Yeah, you could have 2 workers on that particular stage of the pipeline. Yeah? So that's the situation we might have here, that the actual transform bit takes 3 times longer than any other part of the pipeline. So really what we want to do is that transform block actually not going to have 1 thread now, it's going to have 3 threads. But the block is going to adhere to the contract that says, if I receive the message in order 1, 2, 3, after transforming them, I'm always going to output them in exactly the same order. Okay, so it'll adhere to the contract, say, this is the order I receive messages. Even if the other messages are finished early, I'm still going to wait for the first one to come in before I split that one out. So order is preserved down the pipeline. Okay? So here we could parallelize it. A heavy bit of processing here is building up the transform. We batch them, and then while we're sending off to one, we could then be getting ready to send a second batch too. So we're overlapping lots of things here. Okay? The nice thing about this kind of model is the clarity. You'll see that we'll build a series of blocks up. We'll connect them together in a code. And then we'll say, you know what, let's throw 3 threads at that, 2 at that, and 3 at that one. Does it go quicker? No. Well, let's tune it down a little bit. We're not having to massively restructure our algorithm and change things in order to load balance stuff. It's all about declarative programming. Okay, so that's the program space we're going to play. This idea that we're going to have blocks. Blocks will be responsible for doing some kind of logic, some kind of logic that we pass in terms of processing. Could be what we call glue logic, could be buffering, that kind of stuff. And we're effectively connect these together through a series of asynchronous messages. That's the plan. Implementation is TPL Dataflow. It came out in .NET 4. They have a new version 4.5. It's available via a NuGet package. So it doesn't ship as part of the core framework. You have to go and get these bits. But based on the title TPL, it sits on top of the task parallel library. So under the covers, it's using TPL. It's using all the tasks, all that kind of stuff. Let's go and write some code. Okay, so not greedy. Let's not go into greedy. Let's go into producer consumer. So, can you, for me, create me, we're going to do old style programming here. We're going to talk about some of the issues. Create me a blocking collection of integers. So blocking collection, you're happy with blocking collection? This is the old style, this is, so they came out in .NET 4, basically gives me a concurrent collection, okay, which is going to implement a queue onto the covers, but it has blocking semantics, okay. And go and kick off 4 threads, just 4, yeah. No, I'll do 8 actually. A little bit, yeah. 8. Task.run, that bracket goes to consumer, and then pass a new collection. Whoa. 11 things. and build that. Make sure you pick the void version. Okay, go. Should do that one now. Yeah, change it to void. Okay, excellent. Okay, cool. And for that, just do a simple while loop.
Can people see the bottom screen in the back?
No.
No.
You have to raise it up.
You see that?
Yeah.
It would be trouble if they couldn't be able to get up there.
It'd be funny, wouldn't it? Some of them get to the end of the talk and couldn't see half the code. Okay, cold up. Did you want a cold up tag in there? And then just print out the value you took. Yeah. Whoa. Fantastic. And then just quickly go and write me a simple while loop. While true. Yeah, console will rekey. True. Yeah, simple. And then just say col dot add. Yeah. And you can just add a value. New randomness for. Okay. Next. Cool. Okay. I'll run ship it. Enter, enter, enter. I've got no sleeps in there, haven't we? Get some sleeps in there, because otherwise it's going to be a bit sort of new. So go back right. So it's hitting it, it's queuing up. Yeah, and eventually the consumers will come out there 5 seconds and they'll start processing stuff again. So standard producer consumer pattern. Because we use the blocking collection, while there's no items on the queue, what are the threads doing? Sleeping. Yeah? Is this a good thing? Could be worse. Could be spinning, couldn't they? Could say, is there anything in the queue? Is there anything in the queue? This will be really bad. Okay? So they're sleeping. Is this still good? On a server-side application, we really don't want to consume lots and lots of threads. We want to try and use the minimum number of threads for the maximum amount of concurrency. If there's nothing to do, why should we be holding on to a thread, sleeping on it? That's just a waste. That thread could be used for something more useful. The operating system doesn't have to create so many. It doesn't produce so much resource pressure. The problem with this is the consumer's way of sitting there waiting for work. Okay? What we'd ideally like to do is, when there's no work, we'd like them to give it back. Okay? In fact, we can see this real quick. Inside that while loop, let's just print out thread pool usage. Okay, and print out in main as well. Or you print out in there, print out in the while. Okay, so we can see we've dropped down the number of threads. Okay? Yeah? And it's constant. Yeah, that number's never changing. Whether we've got work to do or not, that number is always going to be the same. Okay? So, let's go and kill that. So what we're going to do now is we're going to move this to TPL Dataflow. Okay? TPL Dataflow uses these things called blocks. Go to the slide a sec. Let's just look at this quick slide. So in TPL Dataflow, we have this idea of a block. And a block can receive and send messages. Okay? Type of block on the slide here is what's called an action block. That just receives messages. Okay? But the block, basically an action block, has a buffer. And nearly all of them have some kind of buffer. So you can post messages to them and receive them immediately and then buffer them up. In the case of an action block, you'll supply a piece of code whose job in life is to run when there's a piece of work to do. Okay? But by default, there's only one thread. Okay? So while it's processing that message, it will not be taking any more messages off the queue. Okay? But if there's no message on the queue, you don't consume any threads. Okay? So the action block is going to sit there. It's going to be set up to receive messages. If there's no messages, the thread goes away. If there are messages, yeah, it will start using a thread to process a message. By default, only one message at any one time. Okay? So, a quick change. Do you want to put that away somewhere?
Just that bit.
Yeah, go on, just put that bit. Well, no. Yeah, just put that bit away somewhere. So, instead of doing that, I'm creating an action block. So, this is Dataflow. Action block. Or call it, okay. Yeah, call it consumer. Action block, yeah, of int. Okay, so the action block of int is going to receive an integer. That's the plan. Yeah, I get or whatever val I goes to I don't mind. instead down here where you've got cold.add, comment that out. And instead you're going to say what? Consumer block.post. And what that does is it allows us to post asynchronously a message to the block. This is not going to be walking out the middle, is it? I can cut the screen out. Yeah. Okay, so new random. Okay. All good? Yeah? Okay. So, we're going to get to and yeah, we'll get that. And you put the sleep. Okay. Cool. Right, compile it. So what we've got now, we've got a single action block. How many threads, how many messages will people process at any one time? One. Okay. So you can hit enter many times. 3 or 4. Okay. We're clearly going to consume a thread. Yeah. Okay. Of course, the problem is we're going to have to be where it's going to be quick enough to show us. How many did you put in? You press enter a lot of times.
It's 5 seconds as well. For you sometime.
Yeah, I can kill that. Okay. Right. Just go run it. Run it. Okay. Press enter once. Okay. So we've consumed a thread. Okay. Yeah. After 5 seconds, if you go and hit enter again, maybe it'll come back to 1023. Where are you printing out in main? That's not. Is that inside the while that you're printing that out? Okay.
I've already posted the message.
Yeah, I know. I think we're a bit of a race condition. Okay. Go and whack it up to. Okay. Let's Control C that. Okay. We'll shape it slightly differently. So that will use a single thread. Okay. If there's no threads in use, no work to do, it won't consume any more threads.
Put that there.
Yeah, put it after that. Put it after that. Yeah, and can you go and change it so we know when it's come out and sleep? Make it sleep for a second. And say done. Yeah. Yeah, change the main to while and print out main. Move main above the while.
Or do one there.
Do one above the consumer block. So the 1020, so we've got no work. Yeah, so we've got 1020%. Okay. So there's still 1023, then we posted a message. And when the thread's running, it's 1023. It's done now. Hopefully if you press enter again, it's 1023. Okay? So not worry about why it went to 1021 at the moment. So it went down to 1000, when it's done again, press enter. Yeah, so we're still around this kind of number. Okay? So it's still only processing one message. And when we've not had any message to process, the thread counts back up to 1023. Okay? But at the moment it's only processing one message. We can change it. So on the action block, add a new property, a new parameter, a new execution, yeah, and then give it a value of max degree of parallelism equals 3. Okay. So now we're saying you could use up to 3 threads. So 3 messages can be processed concurrently at this point. Go run it. Okay. Enter. So it's still only dropped 1 because only 1 message. Press enter a couple more really quick. So now it's dropped back down to 1021 at some point, and eventually it will recover back. Enter. We're back to 1023. So effectively, as a block requires a thread, it gets one. If a block doesn't need a thread, it doesn't consume a thread. Trying to build that yourself, just that little bit, will be kind of tricky. But at least you've got ability now to have blocks that can process things asynchronously. They're waiting for work, but they're not sleeping on a thread. Okay? And just from that in itself, that's quite a powerful programming constraint. Okay, those slides. Okay, so effectively that's what we've done. A couple of things about the blocks. You can tell the block when it's complete, when it's expecting not to get any more messages, and then there's a property on the block as well, completion, which is a task. You can wait on that. When it's finished processing all the messages in its queue and what it's outstanding, that will mark as completed. So that's how you kind of coordinate things, and we'll talk about that next. Okay. There's quite a few different types of blocks. We've just seen an action block. That's generally at the end of a graph in terms of processing. We've got a transform block that takes something, a message of some type, and then it's supposed to produce something of another type. So an action block takes an action of T, a transform block takes a function that takes something of T input and produces T output. Okay. We've got a transform many block that takes something of type T input And basically your method has to then return an IEnumerable of T output. Yeah, so a single input and you produce many things going back. The idea is you link these blocks together. Yeah, so if I have a transform block which I post a message to in, and I link an action block off the end of it, once it's transformed it, produces output, it will automatically pass that on to the action block. You won't be physically passing messages. There's a whole pile of glue blocks. These glue blocks, well, provide things like buffering between blocks if you want to buffer stuff up. There's things like broadcast. The broadcast block always has a value. You can read from it many, many times. Normally, most messages you can only read once. Okay, so as you wire things up, you do once. Join block, I will play when we do the Dynamic Philosopher's problem, where we can say, I need to take a message from that block, and when both are available, take it forward and pass it on to someone else. Okay, so we can build quite a lot of programming constructs that we find in sequential code purely from these kind of glue blocks. Okay, let's go and write some code. Let's move to image processing. Okay.
Image processing app?
That'd be the one. Yeah. Set that as a, yeah, okay. You might want to set that as the target project because we, yeah, good. Okay, let's go, buddy. Okay, this is Andy's UI skills at best.
A nice red.
It's a nice one. You like the red? Yeah. I can't remember the reason behind the red. Okay. Unlike your big sexy button, if you put the arrow in there, it's still red. Yeah. Okay, so if
you made it, I'd change that.
If you open the images section, don't do it twice. How many times do you have to click? Once.
Well, that means multiple times, yeah.
Just once. Just once. There you go. So it's just showing you in a tree view a list of images. Right? Richard clicks on one of them, not the sheet because that takes a long time, and clicks the add button. It's going to be changing into grayscale. If it tries to use the UI, it freezes. This is not good. It's not fast and fluid. This is not what we want. Okay? What are you doing?
Okay.
Right. Okay. So we want to make this asynchronous, and there's lots of ways we could do this. But we're doing the TPL Dataflow talk, so we're going to do the TPL Dataflow. So close that. So if you go to the image processing assembly, yeah, inside there's image transform. Yeah, cool. There is a method in here called create grayscale image. That's a synchronous method. We want an asynchronous version. So copy the signature and just add the magic word async on the end.
Does that make async?
If that was all you had to do, that would be awesome, wouldn't it? It's got to be on the top list. You're done, right? Oh, only the compiler could just infer that. Okay. Okay, so what we're going to do here is, well, we basically want to create a block that's going to do this transformation for us. So you scroll up a bit, just above that, create a private field called transform block. And a transform block, in this case, is going to convert to grayscale. So it's going to take a path to an image, and it's going to spit out a bitmap source. That's the plan. Okay. So string, and it's going to take a bitmap source. Okay, and to gray. Okay. No, don't create those. Okay. Next line. So that's a transform block. Okay. So it's create a constructor. And nim it up in there, so too grey. You're all happy with the spelling of grey? Yeah?
What, proper one?
Yeah, I had to go for an entire book replacing grey like that to G-R-A-Y. Can you imagine which nationality was publishing the book? Okay. And then what we want to do in here is, this is a transform block. This takes an input and produces an output. We need to give it a function of what type? String to bitmap source, right? Sorry?
Got one here then.
Yes, you have, yes.
Who's going to put that then?
I think you could probably, but yeah. I've simplified it a bit. I'm not sure you can get away with that. You might have to see S goes to because of getting confused about tasks. Yeah. Okay, okay, cool. Yeah? So the idea now is inside create grayscale image, what are we going to do? We're just going to say toGray dot post. Okay, and we're going to post the file. And effectively that transform block is going to process it. The problem is it's got nowhere to put it. So once it's processed that first bitmap source, it's not going to do it and process anything else until it can hand it off. Okay, so it has to be consumed. Yeah? Okay. So I need to create another block here that's going to consume the bitmap source. And its job in life is to get it back onto the UI. That's the idea, we want it in the UI. So here I'm just going to create an action block of bitmap source. Okay. Block map, bitmap. Okay, and that's going to say I'm in publish image. Awesome. Okay, let's go and new that up. So I say publish image. Publish image equals new action block. Yeah. And then here you go, BMP goes to. Now somehow I'm going to get back onto the UI. And there's a few techniques we can use here. I'm going to use one earliest. First thing we could do is we create an event. So just go and create on this image transform, create a public event of image transform completed arcs. Event handler. Yeah, image transform. Yeah. Publish. Images I don't mind. Image complete. Yeah. Completed. And warrior. Cool. And then all you can do inside here is just fire the event. Yeah. So all the action blocks are going to fire the event. The UI infrastructure is going to subscribe to the event. When the event fires, it's just going to add the image to the UI stuff. Yeah. And then put in the BMP. Cool. Okay. Does that compile? Compile? Compile. Whatever.
Return.
Return from.
It's returning bitmaps.
Oh yeah, turn to void. Yeah, don't grab the signature. I was stupid. Okay. Obviously, we need to link these things together. So inside the, after you create the two blocks, you need to link them together. To link them together, we just say after that. Yeah, after that. Next line. To grey. Dot link to. Yeah. Publish image. Okay. So we create two blocks and we link them together. We post it into the transform block. It does some processing. When it's finished, it passes it on to the action block. Job in life is to publish stuff. Okay. Which thread do you think these blocks are running on? Well, I've said it's TPL under the covers. By default, the default scheduler in TPL is the thread pool, right? So we're going to fire an event from a thread pool thread, and the UI is going to receive it, and it's going to attempt to update the UI. What's going to happen? It's going to crash, right? Okay. Yeah. So we don't want to see that really. So I want to basically say to the action block, do not run on a thread pool thread. I want you to run on a UI thread. So the easiest way to do that is to pass some execution options to the block and say the task scheduler is task scheduler from current synchronization context. So we've got multiple blocks here, but they're running in different contexts. So we can use one scheduler for one block and a completely different scheduler for another. You can write your own schedulers in TPL, so you can schedule them whatever you want. Okay. Final thing we just need to do is flip to the UI. Not in this view model. Let's just go and wipe it. So where are you? Scroll down in the view model.
Yeah,
Scroll down. Keep going. Keep going. Just wipe up in there.
Okay, so image transforms is over here.
Yeah. So just say image transforms. Yeah. Dot complete. Image complete plus equals. Right up in line, yes, there you go. Transformed images, dot add, args dot result. Fantastic. Okay, compile it. Now, scroll down to where we add the image. Oh, no, don't run it, we haven't changed it to use the async version yet, have we? And comment those two lines out. Yeah, and now just say, image transforms dot create various with async. Async. Okay. Yeah, so just a normal async style pattern with fire and forget at this point. Yeah. Okay, so we call. Okay, compile and run it, ship it. Okay, images, click once. Only that was asynchronous, yeah. Image one, click add. Right, move the UI around. The UI still moves around, which is good. And Rich can click on a couple more pictures. His favourite ones. Moving window around. Yeah, it's working fine. You wrote up task manager at any one point, how many calls would be being hit? Yeah? We've submitted lots of work, but their transform block and the action block by default only consume a single thread. So if we say, well, actually, for this part of our application, this kind of processing, I'm happy to use multiple cores at this point. Okay? So we could, if we wanted to, decide to configure the transform block to take multiple cores, right? Because we've got them available to us. So close that, and we just go back here, and then simply, we know the pipeline works, we've tested it, we can see it working sequentially. All you do now is declaratively say, actually, you know what, let's throw a few cores at this way. Okay? Degrees of power 4. Okay? It's good having a time check like that, isn't it? It's pretty accurate too, isn't it? Okay, go. So go images. Bring up task manager, probably a good idea. Okay, go images. What are you doing?
Just check there's noise on top.
That's a default. Okay. We click on a few. Add the sheep. Add the sheep. He's added the sheep a few times, notice. You like sheep. Okay. So you added some stuff after the sheep. The sheep's a big JPEG. It takes a long time to compute. Okay. Yeah. I got 4 real cores, 4 virtual cores. So it's maxed out at the moment. It's got lots of work to do. Yeah. You'll notice you're now doing the sheep. Yes. Another sheep. Yes. Did all the others in the end? Those last 3 were really quick. But because you added the sheep first, even though it might have already finished those ones, they'll be waiting behind the sheep. Be careful. So yeah, so queue up the messages one behind each other, okay? So it doesn't matter the order. The order in which he adds them is the order they're going to come out in. And it might be ready and ready to go, but if there's an earlier message went in and it hasn't been fully processed, the others will be delayed until it's processed. So it preserves order. Okay.
Can I ask how does it relate number of threads with the actual thread coordinator? So who owns?
So it's just tasks it's pinning up, right? So when you say max degree of parallelism, that's the number of tasks it will invoke at any one time. Now, how tasks get mapped onto threads, that's up to TPL. Yeah, so it's just really max degree of parallelism in terms of inside the potential. Notice the word max, it might not be that. Oops. Okay, so that all works. Okay, so we could do something a little bit more elaborate now. We could say, rather than Rich having to click on individual images, it might be nice if Rich could click on, what do you reckon, a whole directory. Yes? Whoa, scary. And go add, okay? Now, we could do this by, inside the UI thread, iterating through the directory, finding all the files, and then adding, posting them. We could do that. Or we could do it in parallel. Which one would you like to do? Parallel. No, it's all on the UI thread. So what we could do is we could create another transform block that we could add to the network here. This one's going to do a transform many block. Yeah? We're going to post a directory, and it's going to spit out a series of files. And we're going to wire up that one to our other transform block. So we're building up a bit of the network now. So we're going to build up a network of. So we're going to have this is our original one, this is our transform block, this is the 2 grey, and there's our action block. And originally we were just posting here. Now we're going to have a transform many block. We're going to post a directory to this, and we're going to link that up to that thing. Yeah? Okay, so we're just basically composing the network. How far you gone? Okay, so inside here, can you do for me return? Actually, no. Create a new directory info because we're going to extend this. So var and equals new directory info. Okay, s. Brilliant. Okay, and then can you for me say return dir.get files. Quote.star.csv.
What's CSV?
Star.csv.
What's CSV files?
Yeah, no, it's JPEG, sorry. Wrong, don't I? You could have just typed JPEG and ignored me. You know what we're doing. My kid don't. I know, every opportunity. Okay, select. Yeah. No, F. No, we're not doing F. No. FI goes to. Okay. F dot for me. Fantastic. Okay. So now what we need to do is just wire it up. Okay, so scroll down. Okay,
so
inside here, where do you do the wire ups? Yeah, there. So go process directory, link to grey. Okay, all good? Okay, we get given a path, we only want to post it to different things. So let's have the line above that. If directory.exists path, then I want you to post it to the process directory. Post path. Else post it to that. Yeah, so we support both. If you give us an individual JPEG, well, I'll post it directly to the transform block. If I actually give you a directory, I'm going to post it to the directory block. Yeah, all good? All right, compile, ready, ship it. Right, go and open up images. No, just open it up. Click on sub, open that, now click add. So hopefully now, this is adding a whole series of blocks to it. And there we go. Yeah, all good? So we could go for the ultimate Uber demo. Click on images, click add. And that should do add loads, right? That's the UI still works. An image appears. Yeah, UI still working. One image. If Richard looks at that list of images, there's one that shouts out to you. Scroll back up. Stop. Bad image.jpg. Notice there's no thumbnail. Why do you think that is? It's not a JPEG. Perhaps it's a CSV file. Could be. Okay? Masquerading as a JPEG.
We've got to wait for start with CSV.
Yeah. So, what do you think might be happening here? We've clearly processed one of the images. We haven't processed any more. Basically what happened is we hit the bad JPEG. Yeah, when it tried to process that, the transform block threw an unhandled exception. Once a block throws an unhandled exception, that block now cannot handle any more messages. Okay? Yeah, so exception handling says if the block throws an exception, as far as it's concerned, the block is done. If you look at the completion status of the block, it's in the state of faulted. Okay? If you post messages at it, then you effectively will just be, well, I think they reject them at that point, but effectively you will not process any more messages once that block has run to a faulted state. Okay? So a couple of ways you can solve it. Obviously you can write it, we'll see a bit later on, you can propagate stuff down the pipeline and identify this. Alternatively, generally you put exception handling inside the block. If you can handle the exception inside the block, life is good. If you can't, then obviously you will have to tear down the whole pipeline. Okay. So we're going to handle it inside the block. So can you create for me another method called safe grayscale image, returns a bitmap source, copy the signature from the line below, call it, put safe on the front of it. Safe. Yeah, I won't just wrap that.
Scroll down a bit, like.
Yeah, up, yeah, good. Okay, and inside there, just do a throw, do a try-catch. Throw, just try-catch. Okay, swallow the exception. That's what you all do at work, right?
That's safe.
Super reliable code.
That's what we were saying.
Yes, awesome safe, totally safe. Okay, and then we're just going to say return. Yeah. And just say return null somewhere. Okay. And then wire up our block to use that. Yeah, so the important thing really is about this is you do need to deal with the error inside the block. If you don't, yeah, the block is done. Okay, you can't use that block anymore. Okay, so you get deadlocks in your pipeline. Did you use that piece of code instead? The create safe one? Oh, you did? Okay, you did that quick.
I know my type is slow, but I can just type 4 letters reasonably quick.
Sorry, man. That was bad. So hopefully. Huh? Are you sure you reached the safe? Oh, there you go. Oh, of course it was a sheep, wasn't it? Holding everything up, yeah. Okay, so there you go. So there's a sheep. Yeah? All happy with that? The problem is at the moment is our directory is only how deep? It's only going 1 deep. Would it be cool, wouldn't it? Okay. Your level of cool has to be kind of geeky at this point. What would be cool is if you could do subdirectories. That would be awesome. Okay? But again, do you want to process subdirectories on one thread or in parallel? In parallel. Okay? So what we want to do now is really want to do this. If the transform many block has found JPEGs, it sends them off to the transform block. If it finds a directory, where does it want to send it? Yeah? So we basically want to send it back to ourselves. So we can build recursion. Okay? So, to do that, go back into here, go back to the linking bit. So here we say process directory.link to. Okay, so we said to, great, put another line underneath it. So now we've got two, don't do anything yet, we've got two link tos. Okay? Now at the moment, we want to link that one to where? Process directory. Now at the moment, this will have no effect. Okay? Because what's going to happen is, when process directory has something it wants to publicize, it offers it to the first thing. And by default, blocks are greedy. They have an infinite unbounded buffer. So it doesn't matter whether that 2 gray is busy or not, it will always accept more stuff. It's greedy. Okay? So this would never fire. Okay? Right. What we can do is we can also provide predicates. So I can say I only want to send it to that one if it's not a directory. So I'm going to say provide a predicate that takes the output type, which in our case is a directory path, which is a string. Say not direct. No, we don't want to do that one, do we? Change it. We want to move that one to the top. Okay. So directory, put a predicate in here, comma, directory exists, and just directory exists. So there's a method called directory exists, which you've already seen. That takes a string, it returns true if the string you provided is a directory. So what that's saying now is, if you got a message from the process directory, if it's the output path is a directory, send it back to yourself. If it doesn't match that predicate, it then offers it to the next thing you link to, which is 2 gray. Okay? If that's happy to accept it, it'll happen. Okay? All good? Yeah? So we build recursion now. Not only can you build recursion, you can see you can also, by linking like that, you can do if else logic. Yeah? So you can have blocks fanning out from each other. Say if the message is of this type, or the message contains this data, send it to that block. If it contains this data, send it to that block. So standard programming constructs, if else, switch, recursion, all handled with blocks. So that allows you to take existing sequential code and map it onto blocks. Those same programming paradigms are available in blocks. Have you done that?
Yes, so
Well, we haven't changed the code yet to do recursion. No. We'll notice we're only getting JPEGs. We're only getting JPEGs.
Oh, you're right.
Yeah. So at the end of that, do dot. At the end of that return statement, do dot.
Here.
No, new line. Sorry. New line. At the end.
You said dot.
I know.
How's that going to work?
Give it a semicolon. Oh, jeez. Oh. We only did this demo last week. Okay, concat.
You do it this way.
No, we didn't. I thought this was cool. Okay, so I've lost the plot now. Dir dot get directories. Okay, good. And then you need to do a select again. Dot F goes to full name. Cool. Okay, we're happy? Okay, so compile it, run it, ship it.
Expecting to see those two now going.
Yeah. As well as basically everything. Yeah. Let's hit it then. Okay, so hopefully, fingers crossed, bear in mind the sheeper issue. Yeah, the calls are still busy though, right? Because obviously you've got work to do. And eventually, there you go. And hopefully we should see. There you go. Okay? Yeah? So we've done the entire, the standard computer constructs, we just written with blocks. Yeah? And the nice thing is any one of those blocks we set inside, yes, it's okay for you to run in parallel, we can make them run in parallel. Order of messages, 100% preserved. Important thing is, if a block has an unhandled exception, the block stops processing. So you really generally try and handle the exception inside the block. If it's a fatal exception, you have to basically propagate that exception and tear down the entire graph effectively. Okay, any questions on that? All good? Question? Is it just the actor model? Now there'll be some serious computer science bots that will basically lynch you for saying that. They reckon this isn't, but there's a lot of analogies to it, and lots of people try to do actor kind of stuff out of this, and you can. And we'll try and do something kind of similar to that at the end. But yes, A lot of people draw analogies. If you look at languages like Scala, Erlang, and all that kind of stuff, they have a very more sophisticated implementation of actor-based stuff. So the guys at Microsoft say, sheepishly, yes, you can build actor-based systems with this, but they don't want to say it's actor-like because all the computer science guys will just jump on it. Right? But yes, you can build actor-like style stuff. Actors are like autonomous things that run, receive asynchronous messages and stuff. And lots of people try to build their own little libraries on top of TPL to do that kind of stuff. Yeah, but generally you go for languages like Erlang and Scala that have that kind of stuff built in. Any other questions?
Yeah. Does it have to be structs, types, kind of given class? If it's any class, you have to take care of synchronization for the things that you're passing through the tags. So I guess, because this seems, you know.
These things you mean, do they have to be value types?
Yes.
Not value types, these are classes, a bit more sort of.
Yeah, okay. If it's a different source, you're going to have synchronization problems if you try to modify this transform block. So you're going to have.
Well, as long as everything's,
You shouldn't.
well, as long as you're passing it along the pipeline. So when someone creates it, only one person, if you know the way you build it, only one block at any one time will ever hold a reference to it. As long as you maintain that model, life's good. If you adopt a functional form of programming, then life is okay, right? Yeah.
Sorry. Can you go back to where you had that predicates? So you wanted to either
The linking bit.
yeah.
Yeah.
Okay. So what happens like if it's not a directory and you want to link a whole, instead of just having process directory dot link to grade, you want to have like a whole bunch of lines. So if it's not a directory, you want to do all this, otherwise do all this.
Mm-hmm.
How?
So that's the way it's working, right? So
Well, directory does one thing. Yeah. So if it's not a directory, it'll jump to that. Yeah.
yeah,
Okay. Just say you want to like go down one pathway or go down another pathway.
that's what you're doing here, right?
Um,
So you're either saying if it's a directory, I'm sending it back to myself, yeah, which is the same as going down another pathway, right? It's another block. I'm saying link myself to myself only if the thing I publish is a directory, okay? If I don't, if it's not a directory, the next link to is this one. This is unconditional. This will always go. Yeah. So this is if else. You can do if else if by having another one of these lines in here with another predicate.
yeah.
Okay? The important thing you need to be really careful of, if you only have link tos purely based on predicates, yeah, if there's any possibility any one of those predicates would never fire true, you now block the pipeline. Because it can't offload that message, it can't process any new messages, so the pipeline's blocked. So best practice says you should always finish with an unconditional link to. Yeah? Otherwise you could eventually end up in a situation that messages match none of the predicates, it can't offload the message, it can't offload the message, it can't process any more messages. Does that answer your question?
Yeah. It's right.
The thread's gone, right? It's the processing thread's no longer not, it's just sitting in its buffer. It's saying, I've got stuff, okay, I need to offload, I can't process anything else. Yeah. Well, if it gets more work coming in, it can process stuff, yeah? What it can't do is offload it, so it's buffering up, and eventually you're going to get an out-of-memory exception. Yeah? Eventually. Yeah? Question?
Can you link to on an exception?
Can you link to on an exception? Well, obviously, what you could do internally, I mean, there's other mechanisms for doing this we'll come on to, but what you could do is you could capture the exception internally, and the thing you propagate out could be an object which contains information say, actually, I had an error, what do you want to do down the pipeline? So you could propagate the error down to the image processing if you wanted to. So rather than passing a bitmap source that could probably more complex object, had a bitmap source and an exception property, and if the exception property was null, I'd fire the event with the exception property as opposed to bitmap source. Yes, I could do that.
I don't know if it was uncovered or not. Can you specify that you don't want to wait for the proper order?
No, order is preserved, there's no way around it. If you don't care about order, this is not the tool for you. Yeah. Actually, there's other ways of doing it. If you don't care about order, we'll come on to it. You could basically have a buffer block and multiple action blocks all running the same code. Yeah, and then in which case you don't care about order. So there are ways of doing it. So we're going to come on to this one. We're going to run out of time if we're not careful. But at the moment, I can have one action block, yeah, and I could run multiple threads here, yeah? Yeah. Now, obviously, the order in which messages come in, 1, 2, is the order in which action block, transform block, is the same order the message is going to go out. Yeah. Alternatively, what I can do is I can build a buffer block, and then I can have an action block, and another action block, only one thread each. Yeah. And so what happens is now they come into here, whichever one of those is free gets the message and it processes it. If this one comes free, gets the next one. It could be this one finishes processing too before that one does, and you could wire this up here to another block here. Yeah. So you can change, if you don't care about all of them, you can do that. Last question, because otherwise we're going to be way behind.
Any thoughts on the overlap with the reactive extensions?
There's a massive overlap.
Yeah.
Yeah. So the team basically said yes, there is a, but they're generally for two different types of things. Reactive is more about event-based processing. This is about compute, really, but there is a massive overlap. Things like buffer block, broadcast, batching, all those things have analogies. The thing about all this stuff too, all those blocks are observable. So if you want to take a transform block and you don't want to wire up an action block anymore, but you can subscribe to it with reactive. Yeah, so I think if you go to one of the blocks, 2 gray or something, in line somewhere, 2 gray dot subscribe, has it got subscribe on it? I haven't got reactive in here, have I? Oh no, 2 gray as observable. That's it, as observable, and then you can subscribe to it. Yeah. So you haven't got reactive in here, but effectively you can subscribe to it. So it bridges into reactive. Yeah. But there is an overlap in terms of functionality. Okay, right. How long have we got now?
We've got 40 minutes.
Wow. We're way behind. Let's go slides. Okay. This is the kind of thing we just built. Yeah, we've basically got pass image into a transform any block, or we can still use the existing block. Okay. Yeah, we can configure concurrency in any one of these blocks in order to give us that behavior that we want. Okay. We can obviously have linked and build multiple blocks. So here we go, right in the transform input. Yeah, it's processing some input. That can only happen. And then effectively you can link to 2 other blocks that can send to 2 different targets, do some processing if they want to, and then you can combine the results at the end too. Okay. Oops, go back one. One thing to watch out for here, this doesn't scale as you might think. By default, each of these 2 things here, the action blocks, would have an infinite unbounded queue. Their default is greedy. Okay? And because they're greedy, if you link these 2 up here unconditionally, this dude here will receive every single message. Doesn't matter whether there's no activity happening on here, this dude will get it. So an unbounded queue. The link to happens in the order in which you link them up. It's got an unbounded queue, it will receive everything. Okay? What you have to do is set the bank capacity on the action block to 1. Okay? Which means it'll only ever receive 1 message. Yeah? If that's busy processing something, it will get offered to that one. When both of these are busy, this guy here will just buffer stuff up. Okay? Great, let's go. Okay, we can link conditionally, which is what we've just seen. The important thing is just make sure the last link to is unconditional. Make sure there's always a place for a message to go. Okay, you can have something called a null target block. It's like if you do it with Unix, dev null. Yeah, equivalent of dev null in Unix. Okay, just link to that, and it will just swallow everything. Okay. We've seen recursion. You can link back to yourself. Okay. What to do? Should we do dying philosophers, and if you've got time, come back to pipelines? Yeah, so skip some slides for me, just jump through to the end. We'll try and cover them. Well, go back again. Go back again. Okay, we're going to do dying philosopher, and if we've got a little bit more time, we'll come back and do some other bits. Dying philosopher's problem. Here we got, how many philosophers? 5 philosophers. Between the philosophers, this is simplified, I guess, they are chopsticks. Okay? In order to eat, the philosophers have to use 2 chopsticks. Trying to eat with 1 chopstick is kind of difficult, isn't it? You can do it, you can stab stuff. Yeah. Which is what most people do when they first see chopsticks, isn't it? Yeah. There's a nasty.
Doesn't work for rice, though, does it?
Doesn't work for rice. When I was young, the first day me and May went on to this girl, she'd never been out to a posh restaurant. We took her to a Chinese, and she was worried about chopsticks. And Mark said to her, "Don't worry, you can ask for the knife and fork extensions. They just screw on the end of the chopsticks." And this poor girl put her hand up and we had to just grab it before she embarrassed herself. But anyway, so we've got these chopsticks here, and for a philosopher to eat, they have to have 2 chopsticks. However, there's a slight problem here, isn't there? Because we've got 5 philosophers and 5 chopsticks. For them to all eat at the same time, we'd need 10 chopsticks. Yes? Okay. So the classic dying philosopher's problem is this. The problem is if each philosopher sits here and grabs the one on their left first, okay, and says, right, I'm not giving this up until when? Until I've eaten. And to eat, I need another one. But this dude here says, I'm not giving up mine until I've eaten. And this dude's at mine until mine. So they've got a deadlock. And all the philosophers, is start. Okay? And there's lots of algorithms we can use in computer science in order to solve this problem. But effectively what we're going to try and use now is to use TPL Dataflow to solve this. Okay? And that's the idea. So, let's go to a project. I think it's called Dying Philosophers. Okay. Okay, so we've got a couple of types here. So let's have a quick look. Chopstick. Chopstick type's really easy. Yeah, just Chopstick has an ID. Okay. As they all do. And I'm a fan. It's a common property, yeah. And philosopher, I don't think it has any code in there at all. No, that's good. Okay, and then program.cs. We said we're going to run with 4 philosophers to start. So the way we're going to model this is this. We're going to have, between each of the philosophers, as where they sit, we're going to have something called a chopstick provider. And that's going to be a buffer block. Okay? What does that matter? Like, just run with it, okay? Just imagine there's a box of chopsticks. Although there's only going to be one in the chopstick box, there's just going to, okay, just...
Yeah, all right. Yeah.
Okay, you got this. We're short on time. And behave. Buffer block. No, come on. Chopstick providers. Come on, this... Chopstick. Let's get equals new. Buffer block. Okay, a chopstick. That's an array.
Chopstick array.
No. Chopstick.
Oh,
Square. It's a buffer block array. Yes. Okay, and it's number of philosophers. Okay, so we're always going to have as many chopstick providers as we offer. Now we're only going to put one chopstick in each chopstick provider. Okay. So then do we for loop. Okay, and that's going to go around to n philosophers. Yes, cool. And then initialize the buffer block. So a buffer block is it's just basically a buffer. You stick stuff in, and you can have things linking out the buffer. Yeah, and if they're available, they'll take something with the buffer. If not, it'll stay inside the buffer. That's the plan. Okay, and then what else do I need you to? And then I need you to post a chopstick into each one inside the loop. Yeah. So chopstick providers. Equals, new chopstick, and give it an ID of I. Okay, cool. Okay, excellent. So what have we created so far? We've just created these buffer blocks that we sit around the table, each one looking the same, one chopstick. Yeah? Okay. Now, can you for me do an array, do another for loop? Yeah, I to n philosophers. Okay, I want you to new up a philosopher. Let's new it up. Yeah, pass in as a constructor. I want you to pass in chopstick provider square bracket I. So each philosopher gets told, here's one set of chopstick providers, and here's another one. It's left and right hand side, effectively. Yeah. And then chopstick providers square bracket I. Square bracket, open bracket I plus 1 modulus n philosophers. Now, I don't know whether we need brackets here. You tell me, you're the mathematician. Okay. And then can you also, right at the front, give the philosopher an ID of I as well. Okay. And then at the end of that, enter. End of that line, dot start. Yeah. Open bracket, close. So we can't. And then, passing, yeah, that's fine. Yeah, that's fine. And then, get rid of the semi. Okay. And then, yeah, you all happy with that maths? Yeah? So the idea is to just wrap it round. Yeah? Okay? So philosopher 0 is sharing his right provider with the other dude. Yeah? The one here. Yeah. Okay. Right. You done that? Yeah, create constructor. Brilliant. The power is sharp. Okay, change that to ID. Okay. Change the next field to next one left. Change the next one to right. Yes, fine. Right. Okay, all good? All happy with that? All looking good. Okay, here we go. So,
install all these?
Yeah, store them away. And I have resharp installed, so
that's handy.
It's very handy.
I would struggle with resharp install.
Okay, cool. So we create a philosopher. Now go and get rid of that because that won't do well. Okay. Now go and add me a method called start. and quickly go right to the top and go and create another action block. Yeah, just create an action block. Call it, I know, body block. This is where we're going to run the simulation of the diners. And what do the diners do? The philosopher does what? He thinks, he gets hungry, and he eats. Okay? Okay? And he goes from thinking to eating real quick if there are 2 chopsticks. If there's not 2 chopsticks available, he goes hungry, and more hungry, and hungry, and hungry, and hungry. And if there are 2 chopsticks available, then he eats. Eat takes a period of time, etc. Go and add for me another method inside there. It's private. Let's say void status change. Okay, that takes a status string. Okay, just print it out in the console. Thank you. Say ID. Put the ID out and everything else. Totally. Cool. Okay, now go and write the body block. So inside philosophy, new body block, new action block. I don't care about the string actually, it's just ignore it. Yeah, it goes to. There we go. And inside here, lifetime of philosophy is while true. They live forever, apparently. Sorry? It is. Okay. So scroll down a bit. Okay, so inside here, what do you want to do? You want to say something like status change, and say thinking. Cool. And then we'll do a thread.sleep. How long do you want to sleep for? New random. Next. What do you reckon? 1,000 to 5,000, yeah? They can sleep up. They can think for as short as a second, as long as a second. Okay, now status change. Hungry. Okay, not hungry. Okay, hungry. Okay. Now at this point, we want to get the chopstick. Do we pick one chopstick up and then pick the other one up afterwards? That would be bad. We'd end up with the race condition, wouldn't we? Every philosopher would just grab one, they all got one, they can't eat. What do we actually want to do? We want to grab both or none. So in TPL Dataflow, we can use something called a join block. So above that?
Here?
No, above, keep going up.
Oh, so there.
No, up where you try with the other blocks, right? Create me a join block. And a join block, you give it, there's 2 types of join blocks. There's join block of T1 and T2, and there's one of T1, T2, T3. Okay? And a join block works like this. It will say, I will consume, yeah, and produce you an item when all the things link to me. So if I join with T1 and T2, I have to have 2 things linking to me. When I've got 2 things, I'll tell you about it, and I'll export it as a tuple, or tuple, whatever you want to call it. Grab chopsticks, yes. And okay, and inside there, go and new it up for me before the action block, Okay, new it up. Awesome. Okay. Okay. So got the join block. So what do we need to do now? We need to link things together now. Okay, what do we need to do? We need to say now that left.link2, yeah, grab chopsticks. Okay. And dot the end, target 1. So normally a block only have a single place you can link to. The join block has 2 points. Yeah? I'll show the slides. And that's going to link to target 2. Okay, go to slide 6, just show. Next slide. So this is what we built. Okay? So we've got each of our chopstick providers, yeah? But a given chopstick provider will basically link to a chopstick pair. Yeah, that's what we just built, the join block. Yeah, and so this dude here will be getting from these 2 chopstick providers. Yeah, but this dude here will also be sharing another one with them. Yeah, so we've got 2 different points of combining. Okay, that's code. Okay. So screen go down. So status is hungry. Well, we're only going to move past the hungry state when we can have a pair of chopsticks. Okay. So we can say grab chopstick dot receive async. Oh, receive. It's just a receive. Okay. Yeah. So at that point we block. Okay. So we're blocked, waiting for a join block to say yes, I've got 2 chopsticks. When it's got 2 chopsticks, it tells you've got them. Yeah, and then do a sleep again, just copy it, just change it to 3000. You eat less than you think, don't you? Generally. Me, I don't know about me, I probably eat. So change it to 3000. This is the last one, yeah. Okay. And then that's it, we're good. You okay? All happy with that? Let me just go back round the loop again. What have we got to do once we've finished eating? What have we got to do when we've finished eating? These aren't disposable chopsticks. Okay? This is the most unhygienic restaurant on the planet. Okay? We're just going to put the chopsticks down. Okay? Yes? Okay, so we're going to post them back to the appropriate chopstick provider.
Where do we get them from?
So, when you receive, what do you think that returns? That returns the tuple of the chopsticks. So those are our chopsticks. Okay? And because it's a tuple, we got inside there an item 1 and an item 2. Yeah? So post back to left chopsticks dot item 1, yeah, and white dot post chopsticks item 2. Okay? All good? Does this sound good? Yeah? You all happy with this? Is it going to work? We're going to have some happy philosophers? What do you reckon? Right, scroll down. We good? Think we are? Start would be good. Correct.
Because if it blocks, then we might have
Receive guarantee, the join block will guarantee you get both or nothing. There is still a bug in there. You might be going down the right line. Hold that for. Okay, but the
I
receive.
have a feeling we'll deadlock somewhere here.
It won't deadlock.
Okay.
Okay, it might starve some people, but it won't deadlock. So it
So
guarantees.
receive will just throw an exception
No,
in case
it's a
there's
receive. It's
nothing?
blocking call. The join block, okay, will only give you when it's got 2. Yeah.
Yeah, but
So when I say join block.
if all of them take 1, then
No, they
one
can't.
can
No,
take
they can't. So what we're saying is this. Yeah? Okay. So we've got our receive here. Okay? So the join block. So what are we going to get actually? You might actually need to see that. I don't think you can see this behavior. So the join block will only give us something here, yeah, when it's managed to get that one and that one.
So if it doesn't manage to get the second one, just try
The receive will just block. The receive will just block it this way. However, if this one here is trying to take from here and from here, there's a possibility that this dude here could steal this one. Yeah? Okay? Yeah? And then down here, they could repeat this down here. Another join block here. Yeah? So we might have a race condition here. But we'll solve this, so don't worry. Yeah? Okay, so let's all see what happens. So will we just put what's inside there? Just post, that's fine. Yeah, that's fine. Are you running, starting all? Let's go run the code. Did you put, oh, awesome. Did you believe that would happen?
Okay, I think we did console reline here.
Yeah, console reline would be good, yeah. All right, line. Change project. Run it. So basically, it sucks if you're philosopher 1, 2, or 3, right?
0 is a great time.
0 is doesn't understand what the problem is in the dining room. He's heard there's a problem in the dining room. As far as he's concerned, he doesn't see one. Okay, and do you think we know why?
You have to pick him off the.
You have to kick him. Sorry, this is how it works at work. You know, oh, he's eating too much. Give him a good kicking.
Take off the list.
Take off the list. The problem is because he is greedy. Okay? So join blocks by default are greedy. Okay? And what we can do is we can configure a join block to say, at the moment join block, this company is configured to be greedy, which means as soon as something comes available here, it consumes it. Okay? Even if there's nothing available here. What we need to make this join block be non-greedy. If it's non-greedy, then it will only take these two messages once both are there. So they'll either both be available, yeah, in which case it will consume it. So if only one's available, so in this case, if that wasn't available but that one was, it wouldn't take it from here. It would allow this join block here to grab it, assuming that one had one from here. Okay? So we need to configure to be non-greedy. So where are you now? Are you on the comma? Are you already there? Braces then? Yeah. In line.
So why do we only get naught eating and not naught and 2?
Sorry?
Why do we not get the philosopher 2 eating at the same time? Because philosopher 2 doesn't overlap with philosopher naught's join blocks.
Yeah, but the problem is, like, we could end up with this race condition that, I don't know your name. What's your name?
Yeah.
Leon said that you could end up with this situation that they're all like grabbing them one out at a step with each other. No, not bounding capacity. Now that's what we do on an action block. On a join block, we have to say greedy equals false. And this is a great demo for dynamic philosophers, isn't it? Because we're configuring the philosophers to be non-greedy. Okay, let's go and run it. It should be better now. It's not going to 100% work. Let's go and run it. Are more people eating? Yeah, which I think probably fits in right back. Can't see your name either. Can't hear it either. So more people are eating. Is everybody eating? One in three are starving. Yeah. It's their fasting day. So what's happening? Kind of a bit freaky, really, but effectively, we're saying receive on a join block. It's not at the point where we say receive, does it actually go and make sure it can get these things here. The join block's running autonomously. At any point, it can see there's two chopsticks available, it grabs them. So the one philosopher puts down his chopsticks, and if his join block suddenly says, oh, they're still available, I'll grab it. You might need it for later on. Okay? So that's not good. Okay? So really what we want to do is we only want to join when we actually want to eat. There's a couple of ways of solving this problem. There's two ways. We could use, instead of a double join, we could use a triple join. Okay? And the third thing we're going to join on is a message that we'll post to ourselves to say, I'm ready to eat now. And the join block will only consume if there are two chopsticks and you're ready to eat. That would be one option. Okay? The other option is to be more dynamic than that. At the point when we go receive, actually create the join block at that time. Okay? Yeah? So I'm going to do the second one. It's up to you which one you want to do, but that's what we're going to do here. So what we're going to do here is, instead of creating the join block at this point in time, I'm going to add. Okay, scroll down. What we're going to do here is, before that receive, we're going to create the join block. Okay. And then what we do is we want to do this, where you've got the subscriptions still lying around somewhere? Where have you got the subscriptions? You linked it somewhere. There you go. Okay. Go and grab those. Now, what I've told you about linking, but I haven't told you about how to unlink. Exactly the same way if you were in the RX talk yesterday, there's no unlink operation. The link to methods return A, I dispose of it. Okay? So effectively we can wrap this in using. So we say using. Yeah, just using around that line and then nest it, yeah? Or uding. That's for Swedish people. Uding. No. I love braces too, right? Okay. Oh, it's gross, man. Okay,
That's
fine.
what it's designed for.
Okay, right, fine. Scroll up. Let peel the back see. Okay. So we've got a couple of using statements inside here, and then at this point we can put the receive inside. Yeah, but can you bring the chopsticks declaration outside, and you will have to.
No, I can't use var.
I know. It's bad, isn't it? It's going to be a tuple, a chopstick, a chopstick. Cool. And this is how it is. Okay, we're good? You're all happy with that? Okay. So hopefully now we create the join when we need to, and we wire up at that point, okay? Yeah. And then when we call receive on the chopsticks, yeah. And then when we finish our receive, we'll then get rid of it. I guess we could do.
Monitoring every time around. It's the least of your.
Yeah, that's true. Yeah, you can move it. It's scary now. I haven't ran the code like that. Trying to kill my demos, aren't you? Bad boy. Okay. Yeah. Okay, you're right. Hopefully then. So a couple are eating. Can't have any more.
Through eating 0 and 2 are eating.
Everyone's eating. Are the philosophers happy?
Top these dirty chopsticks over you.
Half. That works, right? Okay. Yeah. All good. Yeah. So that's the dining philosopher's problem. Okay. So we effectively use join blocks here to remove it. And notice how many locks do we use? None. Okay. Right. I think we've got time for a couple more little demos, haven't we?
15 minutes.
Can you do one?
Can you do what?
Round by time, so
Oh!
wait for.
Actually, good question. Okay. So the question is, can I receive? Yes, we can put a time in here, yes. Okay, so inside here I could put a time span. Yeah. Okay, so yes, you can say from days, yeah, from days. Yeah, we can put a time span in here. But actually, you know what? That's just a good question because it made me think of something else. So at the moment, from a threading perspective, get rid of the time. Why don't I like this code?
Because the thread blocking for each philosopher.
Yeah, the thread's blocking for each philosopher. We're consuming a thread while the philosopher's sleeping. Yeah, effectively. Okay. So what would we like to do? We'd like to give up the thread. Okay. So it turns out that action blocks, or all the blocks, support async and await. So we can mark a block, action block, as taking a function that returns a task. The block is still the same. If the block can only handle one message at any one time, it'll only handle one message. But inside there, we can do an await, which means the thread's given up. No other message will be processed by that block until it's finished processing that first message. Okay? But it means now we can mix in async and await. So we can do there and receive async and stick an await in front of that. Not there. In front of the async. Okay? So I'll mark the method as async. Okay? So this is an asynchronous method, which means we can use await. Everybody happy with async and await? Yeah? Yes, I will have that. So async and await. When we come down to here, instead of sleeping, we want to change that to a task stop delay and await on that. Okay? You need both of those. Await, task stop delay. You need to go into thread.sleep bit. Okay? So task.delay creates a task that is completed when that timeout happens. Yeah? And the same up here. So now, we're only processing one message, which is what it is, but the important thing is you give up the thread now when there's nothing for the block to do. Okay? So it still supports async. Sorry? You okay? Okay, cool. Just going to run it through, still works. Yeah. But the important thing is we're not consuming threads now, yeah, what they're thinking. Yeah? We're actually, yeah, we're async and away. In fact, we can probably put some wobbly code. No, that's just nice. I don't see it. Okay. Right, all happy with that? Yeah? Okay, let's do one more thing. Let's get back to our image processing. Because we can use async and await as well in one other place. Okay. So, with our image processing application, how are we publishing the fact that we've finished processing an image? We fired an event. You know what? That's just so .NET 1.0, isn't it? It's so don't want to do that. So, it turns out that these blocks expose tasks. Or put it this way, you can receive asynchronously on them, which produces you a task with their result. So what we can also do here is go to the image processing library. Yeah. Okay. Go and add me another method in here. Call it public task of bitmap source, and mark it as a yeah. Just mark it bitmap source. That's all we need. Or botmap. You love your bot maps, don't you? Bot map, bitmap. Next image. No, you can if you want. Yeah, I don't know. Yeah, and inside here. And all I want you to do is here, he said return transformed images, or to grey, wasn't it? To grey. Dot receive async. Okay? Yeah? And what that will do is return the task of bitmap source. Okay? Yeah? So now, if we go scroll down, unlink the action block, where you've got the action block linked up, it fires the event. Yeah, get rid of that bottom line. Yeah, comment down. We're not going to fire the event anymore. Okay? On the inside image processing, the view model, okay, where you up. Yeah, comment that. Okay, write me another method. Public void, publish image, publish images. Okay, mark it as async. Mark it as async, you can use await. Okay, so now inside here, while true. And bitmap source, image. Equals image transforms. Image transforms dot next image. Yeah. So what's that going to do? You just took my nipple off.
It fell off.
You've heard how hard he hits. You can hear him hitting the keyboard at the back, can't you? Lightness of touch is not. Yeah, thank you. So we now call publish image. So what's this do now? On the UI thread, it comes into here and then it doesn't await. Okay? Yeah, when we receive async, return something, eventually we end up back on the UI thread, we just add it here. So it integrates with async and await by returning tasks of things. So in fact, we don't have to use, we can wire up to the end of blocks, not using events, which we just did, and just run a piece of code like that. So hopefully run it, it should still work. We're going to go for the big one. That should still work. We're not firing the event anymore, but we're just receiving async now, and we should start to see the images starting to appear. Yeah? All happy with that? Okay? Cool. What have we got? 5 more minutes? We'll do one more? Let's do the greedy one, just so everybody understands greedy one more time. Okay. Do this for me. Create me 2 action blocks I'm in. Well, if it's linked to something else, there's still carried on by the GC, right? Yeah. And if it's been executing, you'll still have a handle somewhere by the GC. So we've got block 1, block 2. Make each block print out the value of I, saying what block it is. So block 1. Copy paste. Cool. And then put a thread.sleep after each one. Make one of them a thread.sleep for 1 second and the other one a thread.sleep for half a second. Okay, cool. Create me a transform block. It takes an int and int and it squares the int. Items on. Okay. Sharpen screaming now. Okay. Okay, and then wire them up. So can you wire up the transform.link to block 1? transform dot link to. Yeah? So what's going to happen here now? Do a for loop. 20. Cool. And then just do transform dot post. What are we going to see now when we run it? Console will be long. Actually, do.
Post it.
Yeah, console will be. Yeah, no, I was going to say, we've got a console will be long. Okay. What's going to happen when we run this? Yeah, so block 1, right? So it's going to go there. Also, graphical programming never got so easy. Yeah? So block 1. Block 1 because block 1 is configured to be greedy. Okay. To make this work, we have to just see. Okay. Change that to new execution. Yeah, and inside here, it's not. It'd be nice if there was a flag for greedy, like the join block, but it's not quite the same. You're basically setting the bounding capacity of the buffer. So here's the bounding capacity equals 1. Yeah, do the same for the other one. The power of copy and paste then. Right. Okay, go ready now. Now both blocks are executed. Yeah. The problem is with this as well, the transform block can't process any more blocks until one of those blocks are free. Now that's not great. Okay, so what you could do is inject what? A buffer block. Yeah. So what typically see will happen here is that after the both those two, the transfer block will link to a buffer block, and the buffer block then will be linked to those other two blocks. Yeah. Which means the transfer block could always offload. Yeah. To the buffer block, and then the other two blocks, when each one of them is free, could receive. Yeah. Yeah. By not having the buffer block, effectively we block up the transfers. Oh, you put it in. Wow. Bugger block? Buffer block.
That's not good.
So that means that if the output is full, so now one can process the transfer block with full stop to take an input?
Previously, yes. Yeah.
Without the buffer block?
Yes. Yeah, the transform block says, I've done an input, I need to produce the output. Oh, I can't produce the output to anybody. No one will receive it, I can't process anything else.
Okay.
Yeah.
So essentially the transfer block can just run at full speed now, not to worry about
Yeah, because the buffer block looks kind of weird. Why would you have a buffer block if each block's its own buffer? So it's because you want to have this buffer. Yeah. Okay, let's go slides. I'm just going to quick look at a couple of examples. Go back a bit and then we'll finish. Go back. So glue blocks, that's where we got to. Go. Where did we get to?
No, there was where we were there when we started.
Okay. You can say to a block that it's complete, there's nothing else coming, yeah? And then if you wait on the completion of the block as a completion property, you can wait on that. Problem is if you completed the front, when you finish posting something to a pipeline, you want that thing to propagate. When you create a link, go back to code quickly. One of the options on a link, just one of them, yeah, common new. Link options. Yeah, inside there is a propagate, completion equals true. Yeah. So if you call complete on this one, once it's finished processing everything and passed it on, it tells the next one in the chain, oh by the way, that's the last message I sent you. If the next link's marked as that, etc. So you can mark the first one as complete, and you can wait on the end one, and when everything's been through the entire pipeline, the whole thing's done. Handling, I said you have to handle it internally generally. Okay. If you don't handle it internally, you turn propagation on, that final wait that you can do on that final thing will rethrow the aggregate exception, so you will get to see the exception. Glue blocks, these are things like I said, these plugging things together. Receive join. Batching basically says I'll receive up to so many messages, and then I'll forward an array of those things. You can also say to the batch, do it now, do it now. So you can do timed or quantity. Broadcast block. You write a value to the broadcast block. When anybody tries to receive from the broadcast block, there'll always be a message there. Okay, whichever the last one was. Write once. First one to write to that, that's the value. It's like a read-only variable. Yeah, you write to that once, and again, lots of people can receive from that. Oops. We talked about buffers like that. Go. Broadcast block. Yeah, one advantage of the broadcast block here is we could have a couple of blocks here. This block was processing data. It has to process every single value that comes in effectively. Okay? So it will have a massive buffer here, it will process everything. This is configured to be non-greedy, it's write to disk. So this is best effort, right? So whenever you change the value here, this dude here will always see it, yeah, and process it. But this guy is writing to a log file. Well, he'll write one to a log file, and he'll go back and say, is there anything else? If this value has changed, it will write next one to the log file. But it might have had multiple changes inside here, and this guy would have missed it. This guy's got an unbounded buffer, it would have received everything. Yeah, so you can have this kind of model of, I'll do best efforts for logging, but processing, well, I have to process everybody's payroll, but if I don't log anything, no biggie. Right, so we'll build that first. Batching, we talked about. Joining, we've definitely talked about quite a bit. Oh, go back. Yeah, so this is still like a load balancer here, right? You've got basically this node contains, this buffer here contains all the nodes that do the work. And this is the work items, yeah? Scheduler block says I need a work item plus a node to schedule it on, yeah? Once it's got to, it sends to the dispatcher that sends the work to a particular node to do the processing. Yeah. Okay. Similarly, we can have exactly the same thing again, but this time we're going to have a local dispatcher. Yeah? And as long as we configure this to be a non-greedy join, this will only use this scheduler if there's a node available to schedule it on plus a work item. If there's not a node available, and this guy's available, then this dude will get the work item. Go. Okay, so TPL Dataflow. It's a different way of building asynchronous programming. It's a series of blocks. It's declarative. I define my parallelism through a series of autonomous blocks, and I pass messages around. No locks involved as long as each one of those different blocks processes the message. There's no side effects going on. It generally means code gets very simple in terms of how to plug these blocks together. If you suddenly decide this part processing needs more cores, it's a configuration of it, it's declarative. You're not changing the structure of your code, adding more loops, adding more processing here. You just basically declaratively go and change things. Okay? For lots of problems which are inherently sequential and care about order, parallelism is often very difficult. This makes parallelism very easy. Okay? It preserves all the down that pipeline. Okay? So where order matters, this is a very cool piece of tech. Okay, any questions?
You said this will work with .NET 4 and 4.5.
There is a version for 4. I'm not sure if you can, I've seen you can still get it. But
Would you recommend it without actually like?
Sorry?
Would you recommend using this without?
Yeah, I've used it without a way. I mean, in fact, there was a project we were on recently. I wrote the code and then realised I couldn't use TPL Dataflow and use files. We were doing very similar processing, CSV, batching it, all doing this in parallel. So definitely worth a look. I don't know what the state of play is with version 4, but its main target area is 4.5.
How do you unit test this sort of thing?
How do you unit it very high? Well, in some ways, this gets a little bit easier because you can test each block now. Yeah, because you can say it's only running on one thread, and it gets a lot more similar. Linking them all together, that's a bit more integration testing phase. But the nice thing is, each of those different things is a piece of sequential processing. No race conditions inside each block. So you should be able to test the block as an input and the expected output. And as long as you've got no side effects in play, then life gets easier for you. So yeah, you could argue it's far easier. Any other questions? Okay, if you want to know more, we have a book. This is it. It came out in December. There's a chapter.
I was first.
There was a chapter in here, which is my favourite chapter, which is TPL Dataflow. It's available. Does everybody want a copy? Okay, you ready? I'm going to do this blind. I think I feel like the bride, don't I?
First, going to just hit someone in the face.
All right, thank you very much.